Yeah, hello everyone. Today we will cover our first video on Apache Spark concepts. I will be creating more videos on Apache Spark along with advanced level concepts as well in the future videos. So let's start. So first let us understand what is Apache Spark. So if you have already visited my earlier video of Databricks, we have covered that on a high level. We will again revisit that part because the video is on Apache Spark concepts itself. So Apache Spark is an open source, unified, high performance, general purpose, in-memory distributed computing engine used to process large amount of data. So basically it's a open source, unified, high performance, general purpose, in-memory distributed computing engine, and you can use it to process large amount of data. Now let's understand each of these features step by step. So what is in-memory processing? So you can understand that instead of some working with the disk drives, the data is kept in random access memory and is processed in parallel. So as it is processed in memory, so it's comparatively faster. The next is open source engine. So Apache Spark is basically an open source distributed processing system used for big data workloads. So it has an open source community with contributors from around the globe who build different features, perform different documentation, and also assist other users as well. So this is an open source engine. The next is it has APIs in multiple languages. So Spark's language APIs make it possible to run Spark code using different programming languages such as Scala, Java, Python, SQL, and R. So if you know any one of these languages, you can use Spark very easily. Next is Unified Computing Engine. So Spark comes packaged with higher level libraries, including support for SQL queries, streaming data, machine learning, graph processing. So if you know Spark, so you can work with any of these. You can work for SQL, for streaming data, for machine learning. And if you want to do graph processing as well, you can do it using Apache Spark. The next is it's a fault tolerant. So what is fault tolerant? So it has the ability to continue to function properly even if some failure occurs. So RDDs help to achieve fault tolerance through the lineage. As RDD is an immutable data set, it remembers the lineage of the deterministic operation that was used on fault tolerant input dataset to create it. So something, suppose you are working with Apache Spark and at some level if some failure occurs, so you do not need to worry. So RDD, it will maintain a lineage from where it will be able to recover from the failure basically. So from the lineage itself, it will start processing again the next steps. So there is no data loss if you are using Apache Spark. The next concept is lazy evaluation. So what is lazy evaluation? So you can understand from the word lazy that lazy evaluation is a strategy that delays the evaluation of an expression until its value is needed. So until and unless you need to execute it or you need to have that value, so nothing is evaluated. So in Spark, lazy evaluation means that you can apply as many transformations as you want, but Spark will not start the execution of the process until an action is called. You can, we will understand what is transformation in action in this video itself in the later part. So for now, you need to remember that when you in Spark, you can apply as many transformations as possible, but nothing will be executed until an action is called. The next is distributed computing. So Spark runs in a distributed way by combining a driver core process that splits a Spark application into tasks and distributes them among many executor processes that do the work. So we will understand it in a couple of slides when we'll be going through the architecture of Apache Spark. So there will be see there is a driver process, there are worker nodes, where the executor are being run, where the tasks are being executed. So you can understand from there how this distributed computing works. Finally, fast processing. So Apache Spark is almost 100 times faster, you can say, than our earlier Hadoop technologies in terms of data processing. So these are primary features of Apache Spark. Okay, so now let us understand the Apache Spark high level architecture. Okay, so you can see at the base there comes Spark core. You can see, right? So Spark core, and along with that you can see there is resilient distributed dataset, that is the RDD. So resilient distributed dataset is basically the fundamental data structure of Spark. It's a low level API. Okay. So Spark core contains the basic functionality of Spark, including components for task scheduling, memory management, fault recovery, and interacting with storage systems, and many more. So you can also see that there are different APIs are being provided here: Python, Scala, Java, and R. So Spark Core provides these APIs to create and manipulate the RDDs. Okay. So, but it was comparatively difficult uh, to use this in complex operations, and it was difficult to write optimized code using RDD. So if you go through the RDDs and those things, you can see that if you want to write an optimized code, it is very difficult. So for that, the next thing is coming on top of it, that is Spark SQL engine. Okay, so here you can see there are two things: Catalyst optimizer and Tungsten optimizer. So from the name itself, you can understand that it will optimize your code in some or other way. So let's see how it is optimizing. So Catalyst optimizer generates an optimized physical query plan from the logical query plan. So it will actually generate a plan how to execute it physically in an optimized plan basically. So this optimized query plan is then used by Tungsten to generate an optimized code by making use of whole stage code gen functionality, which was introduced in Spark 2.0. So basically it generates a compact RDD code for final execution, which significantly improves CPU efficiency and performance. So using both of these optimizers, the code that will be generated, which will be a very compact one, an optimized one, and it will significantly improve your CPU efficiency and performance. Okay, so we will deep dive into both of these optimizers in our future videos and understand that how these query plans are generated, how this logical query plan generated, then how it is moving to physical query plan. So these are step by step generated. So we will look into these things in depth in our future videos. As of now, for understanding the Apache Spark high level architecture, you need to only understand that these are the optimizer which are basically optimizing your code for better efficiency and performance. On top of it, it's coming data frame and dataset APIs. So data frame and dataset APIs are basically high level APIs. So previously we saw that RDDs, which are low level APIs without any optimization, but in data frame and dataset, these are high level APIs which will be having these optimization options. Okay, so if we go to this definitions, that Spark data frames are like distributed in-memory tables with named columns and schemas, where each column has a specific data type. Spark data frame is like a table. It is basically like a table. When you will be accessing a data frame, you will see different columns, different things, and you can access this very easily as if you are using accessing tables. Okay, so what is Spark dataset? It is basically an extension to data frame API, and Spark dataset provides both type safety and object oriented programming interface, which was not there in data frame. So there are different scenarios where you need to use RDDs, you need to use data frame and dataset based on certain scenarios. We will look into those in details as well in our future videos and understand when to use what. Okay, and these are as I already mentioned, these are high level APIs, and both use optimizers for optimization purpose. As you can see here, on top of it, it is there. And finally, we have different libraries on top of it. Spark SQL, we can use for structured data, Spark streaming for real-time data processing, MLlib for machine learning purposes, and GraphX for graph processing. So on top of it, you can use these libraries. So as a whole, this is Apache Spark high-level architecture. Okay, so let's move to the next one. Okay, so this is Spark application architecture. Okay, so if you remember in our some previous slides, we were talking about driver, worker, and those things. So you can see here, there is a driver node, there is a cluster manager, there are worker nodes within which there are executor within which there are some codes. Okay, so Spark application basically consists of a driver process, as you can see here, and a set of executor process. Okay, so the driver process basically runs your main function and sits on a node in the cluster. You can see there is a driver node. So it's basically, you can say, it is the heart of a Spark application and maintains all relevant information during the lifetime of application. It will have all the information during whatever is the lifetime of the application. It will have each and every information in it. Okay. And what is the role of executors? Executors are basically responsible for actual execution of the work, and that work is being assigned by the driver. This is the driver, this is the worker node. So driver will be assigning the work to the executor, and main functionality of executor is that it will be executing the code which is being assigned by the driver, and along with that it will continuously report the state of the computation, what it is processing on that executor itself back to the driver node. Okay, and cluster manager you can see in between. So it's control basically the physical machines and allocate resources to the Spark applications, and it can be anything. Means it can be a standalone the Spark standalone manager, Yarn, or Mesos. Okay, so this is basically Spark application architecture. Now let us understand a bit in a detail step by step. So you can see, first, Spark application helps in orchestrating parallel operations on Spark cluster. Okay, so this is a Spark application. It helps in orchestrating the parallel operation in Spark cluster using different work executors and those things. And Spark driver basically instantiate a Spark session. So Spark session is used by the driver to access the cluster manager and the Spark executors. Okay, through Spark sessions, it will be accessing the cluster manager and these executors. And cluster manager is, as we already discussed, is primarily responsible for managing and allocating resources for the nodes on which your application runs. So Spark driver instantiates a Spark session and communicates with the cluster manager and request resources which can be CPU, memory, etc. from the cluster manager for executors. So it transforms all the Spark operations into DAG computations, schedules and distributes their execution as tasks across the Spark executors. Once the resources are allocated, it directly communicates with the executors. So you can see a Spark executor runs on each worker node in the cluster. Each worker node in the cluster, the executor communicate with the driver program and are responsible for executing tasks on the workers. And you can see there are different cores. So what is core? A core is the basic computational unit of a CPU. In Spark, this controls the number of parallel tasks an executor can run. So this is basically a Spark application architecture. See, if anyone asks you in the interview itself also, you can explain it in this manner. Okay. Now next, you can see that there is a diagram, right? Driver, from driver, there are different jobs. From job there is stage, from stage there is task. So let us understand how an Apache Spark code gets executed internally. So in this way, actually, Apache Spark code gets executed internally. So driver program basically runs your application. So whenever you execute a command or perform a Spark submit, it runs the application on the driver. And application is divided into jobs, stages, and tasks. The main objective is to maximize the parallel execution. So let us understand step by step. Okay, let us go back. So driver converts your Spark application into one or more Spark jobs and then transforms each job into a DAG. We will understand DAG in a couple of slides later. So you just need to understand that what is driver exactly doing. Driver actually converting your Spark application into one or more Spark jobs and then transforming the each job into a DAG. Okay. Now from jobs, stages are created based on what operations can be performed, whether it's serial or parallel. Few operations can happen in a single stage, as you can see here, and few might need more than one stage. So that totally depends on how the operations are being performed. And now each stage is comprised of Spark task, which is the basically the unit of execution, right? So in task itself, the execution will be happening. So each task mapped to a single core and works on a single partition of data. So this happens in this manner actually. You can see in Executor, there are 4 cores present here. This is a worker node. From here, for each core, a task will be assigned. Okay, so there are 4 cores, so 4 tasks are being assigned here in the Executor. So each task is assigned to a core and Executor performs this task. So in this way actually your Spark application gets executed internally, and tasks are low level components which are executed. A driver assigns the task to the core in an executor. You can see here an executor performs these operations. So it returns the result back to the driver and driver returns the result back to the user. So in this way Spark actually executes everything internally. Okay, so this is the Spark application architecture. Okay, now let's understand what are the different Apache Spark deployment modes. So you can see here there are different deployment modes: local, standalone. You can deploy it in Yarn client, Yarn cluster, Mesos client, Mesos cluster, and Kubernetes. So if it's a local, it will be running on a single JVM. The driver will be running on a single JVM. Executor will be running on the same JVM as driver, and cluster manager will be running on the same host. For standalone mode, it runs on any node in the cluster. The driver, the executor, each worker in the cluster will launch its own JVM. For the executor and cluster manager, it's allocated arbitrarily to any host in the cluster. For Yarn client, the driver runs on the client itself, not part of a cluster. The executor is the Yarn's node manager's container. Yarn's the cluster manager here is Yarn's resource manager, which works with Yarn's application master to allocate the containers on node managers for executors. And for Yarn cluster, the driver runs with Yarn application master. The executor same as Yarn client mode. The cluster manager is same as Yarn client mode. And Mesos, it's run on client machine. The driver not part of Mesos cluster. Executor, it container within Mesos slave. Cluster manager, Mesos master. For Mesos cluster, it's the driver runs within one of the Mesos master. Executor same as client mode. Cluster manager, Mesos master. For Kubernetes, driver runs in a Kubernetes pod. For executor, each worker runs within its own pod, and cluster manager is the Kubernetes master. So you just need to understand these things, that how it works, right? There are different modes where the way you can deploy this Spark in a different modes. You can deploy in local, standalone, Yarn, Mesos, or Kubernetes. These are the concepts that how these things works. So you just need to understand this. So in this way, we will be able to understand that how it actually works if your deployment mode changes. So you can just go through this and you will understand that how it is working. Okay. Let's move to next one. So we have been talking about DAG. So DAG, its full form is Directed Acyclic Graph. So what does it mean? Let us understand. So DAG, its directed acyclic graph, is a fundamental concept in the Spark execution model. From the very first time we are seeing that, right? There is lineage and those things. How if there is some failure occurs, it will be again running without loss. So everything, it's this DAG has its role. Okay. So operations are executed in specific order, that is directed. You cannot come back, right? Directed, and no loops or cycles in the execution plan. So that is acyclic. So that's why it is directed acyclic graph. And each stage depends on completion of the previous stage, and each task within a stage can run independently of other. And Spark achieves, as we already discussed, the fault tolerance using the DAG by using a technique called lineage, which is the record of the transformations that were used to create an RDD. So when a partition of an RDD is lost due to a node failure, Spark can use the lineage to rebuild the lost partition. So let's see how it is actually working. So here you can see in stage 1, we are reading the file. Stage 2, we are filtering it using RDD. Stage 3, we are mapping using RDD. Stage 4, we are reducing it now using RDD. And finally, the output is there. So you can see it's a directed one, right? From left to right. There is no reverse arrow and there is no cycle. Okay. So in this way, you can see this is getting executed. So each stage depends on the completion of the previous stage. So stage 2 depends on completion of stage 1, stage 3 on stage 2, stage 4 on stage 3, and final output is on stage 4 itself, right? So if something happens, so it can suppose a failure happens in the stage 4, so it can again go back to stage 3 and can, based on the transformations, you can uh, again recreate these things. Okay, so this way actually this DAG works. So now let us understand the Spark operations. So we have been also talking about transformations and actions. So there are two types of Spark operations. One is transformations and one is actions. So let us understand what are these. So transformations actually transform a Spark data frame into a new data frame without altering the original data. So whenever you are applying a transformation, the already existing data frame will not be altered. Instead, a new data frame will be created. So it will not change the original data frame, but will return the transform results of the operation as a new data frame. So all transformations are evaluated lazily, as we already discussed what is lazy evaluation, and the results are not computed immediately, but they are recorded as a lineage. So we have already also seen that how that lineage is working, right? So thus it provides fault tolerance. So a lineage allows Spark to modify its execution plan and rearrange certain transformations and optimize them into stages for more efficient executions. So suppose you have done 5 or 6 transformations. Okay, so Spark will try to modify its execution plan based on whatever transformations you have provided. So the execution plan is optimized, right? So in this way, actually it will change its execution plan, because it is actually not getting executed until and unless the action is called. These are all transformations. So you have the facility, the Spark has the facility of changing the execution plan based on whatever transformation you are keeping on adding, right? So in this way, it helps to run it in an optimized manner. And what is action? So action triggers the lazy evaluation of all the recorded transformations. So whenever we will be calling the action, so these transformations, whatever we have provided, will be executed. So let's see what are the examples of transformations and actions. So whenever you will be calling group by, order by, filter, join, select, these are all transformations. So nothing will get executed. But once you call some actions such as collect, save, count, show, take, all these will get executed. So this is transformations and actions and their examples. So now transformations are of two types. One is narrow transformation, another is wide transformations. So what is the difference between them? So narrow transformation, actually data from same partitions are read. So there is no data shuffling involved. Okay, so there is no data shuffling. So basically shuffling is the process of exchanging data between partitions. So data will be exchanged between different partitions. So as a result, data rows can move between worker nodes when their source partition and target partition resides on a different machine. Okay, so shuffling basically is a time consuming operation. So it uh, you can see uh, in narrow transformation there is no shuffling, so it's comparatively fast. And in wide transformations, you can see that data from other partitions are read, combined, and written to disk, and data shuffling are involved. So it's comparatively slow. And if you are asked what are the example of narrow transformation, you can say map, flat map, filter, sample union. So there is no shuffling involved when you are calling this. And when you are calling group by key, reduce by key, sort by key, aggregate join, repartition, there will be shuffling involved. Okay. So these are few examples. There are others as well. So you can see what actually is happening. There is no shuffling. Here there is shuffling, you can see, right? From this one to this one, from this one to this one, but it is whatever it is happening, it is happening on the same partition. So our primary goal should be to use this wide transformation as late as possible. Okay. So in that manner, what will happen if we apply filter at the very beginning, the amount of data will be less, and thus there will be minimization of data shuffling. Okay. Okay, so this that's all for this video. So this was our first video on Spark concepts. So thank you all for joining. Let's meet in our next video. Thank you.